Welcome everyone. Time to move on into the vector calculus part. And before going further into this topic, we'll have to first learn about the differential length, area, and volume. First of all, let me give you a little idea about what differential length or any differential quantity means. Any differential quantity means a quantity infinitesimally small. For example, let's say you have a strap over here and you were told to calculate the total length of it. So let's say you just divide this thing into 10,000 equal portions, okay? Let's say this is one portion, this is another equal portion, this is another equal portion, this is another, this is another. So if you just calculate these individual lengths and then move on to sum all of them together, you're eventually going to get the total length of the strap, right? And basically this is the principle of integration as we know it. So let's say this small length over here is equals to dl, this is equals to another dl, and this is equals to another dl, this is going to be another dl, this is another dl, and so on until you reach the end. So if you sum all of those dl quantities together, you are going to get the total length of the strap. Okay, and you already know about the notation of this sum, right? It's written like this. Okay, so the integration of dl is going to give us the total length of the strap over here. So these small quantities that we've divided the strap into are called differential lengths. Okay, so this is what differential means. This means infinitesimally small. Now let's move on to the differential area concept. Let's say you are given a piece of cloth over here and you're asked to calculate the surface area that this piece of cloth covers. If it was a rectangular shape, then it was easier for you because you know the length, you know the width, and you just multiply those things, and you just get the area. But in case of irregular shaped object, defining the surface area is not that easy as rectangular shape or a triangular shape because it's not regular. In that case, you can take an infinitesimally small area. Let's say the value of the area of this small portion or surface is dA. So the whole surface is basically made of a lot of identical surfaces like dA, right? This is a dA, this is a dA, this is also a dA. And if you just take the sum of all those dA, you will get the total area. So dA, the area of this little surface here, is called differential area of the surface. And finally, if you take a bigger volume, for example, a cylinder or something, let's say in case of a cylinder, you know the height and you know the radius, of course, then you can get its volume by pi r square h. But if this was a irregular shaped object, then finding the volume is not that easy. The let's say let's say the cylinder looks like this right now. So how do you get its volume? So let's say a small portion over here is like this, and if you take the volume of this little piece here, this is dV. So this is called the differential volume. And if you take all sorts of differential volumes and sum them up together, you will get the total volume. Okay. So this is the basic concept of using the differential length, area, and volume to calculate different quantities. Okay, let's jump straight into the Cartesian system to see how the differential length can be calculated using the uh, differential change of the variables related to the Cartesian system as we move from one point to another. So let's say in this picture, the initial position of a person is at point D, and then he wishes to move on to the point Q over here. And this cube, previously we have told you that the coordinates that we are using in Cartesian system make up a rectangular parallelepiped. Okay, so this is the rectangular parallelepiped as we move further away from the D point to the Q point. So this is our initial point and this is our final point. Okay, so the displacement vector, if you want to go from D to Q, will be dq vector over here. Okay, if it's not clear from the picture above, this is the point. The D point is situated on the closer plane that you were looking at, and Q is on the far plane. Okay, so Q is over there. So the dq vector is basically the diagonal connecting dq points. And now let's say dq is infinitesimally small, as said earlier, as we are talking about differential length. So this cube is actually infinitesimally small. So the magnitude of dq is basically in the range of 10 to the power, let's say, minus 57 or something like that. So it's infinitesimally small. And now this dq vector, which is infinitesimally small, we can name it as dl. And this vector sign over here is given because displacement is a vector. So dl, the small displacement, should be a vector. So let's say dq is infinitesimally small, and we can denote it as dl. So dl is a vector, and as any other vector in a 3D space in Cartesian system, we can break this vector down in three of its components. All right. For example, when we learned about the Cartesian system, and vector in the 3D space would have x coordinate, a y coordinate, and a z coordinate, right? And now, GL being a vector itself can also be denoted into its three infinitesimally small components along the x, y, and z axis. Let's say you are willing to go from D to Q point, right? So first, let's say you start your journey along the x axis. Let's zoom this picture over here. Okay, let's say you want to move from the D point to Q point, and the vector connecting these points is dl vector, and we're trying to break it down into its components. So first, let's say you start your journey from here. First of all, you have to move along the x-axis to the all the way to the S point over here. Okay, so you start your journey at D, you move along the S point, you move along the x-axis, and you move a distance equal to dx, let's say. Since all of the quantities are infinitesimally small, so we're always going to denote them as dx, dy, dz, d phi, etc., etc. Okay, so now that you've reached the S point starting from D by moving along a distance equal to dx, you then move along the y direction, start your journey from S and end your journey at the point R by moving a distance equal to dy. And by starting from R, you go along the Z direction to get to the Q point by covering a distance equal to dz. So this dx over here, this dy over there, and the dz are the components that make up what dl is. Okay, so dl being a of 3D vector, we can break it down into the three components. So dl can be written as the sum of the three components of it. So this means any sort of differential displacement vector in a 3D space can be written as its three components along the three axes that we're talking about. And in Cartesian system, the notation will be like this: ax dx is the component of dl along ax, ay, dy being the component of dl in the direction of ay, and az, dz. All right. And later in this course, for different calculations, you will need this expression. Okay, now let's talk about the differential area after completing the differential length concept. The three coordinates of the differential length that we talked about, dx, dy, and the dx, dy, and dz creates a rectangular parallelepiped as we discussed earlier in the coordinate systems part. So let's say this is the differential volume that's created by the differential length change along the three-axis direction, all right? So over here in this closed volume, you have six faces or six surfaces, right? And this differential cube has a length equal to dx, a width of dy, and a height of dz. Because dx, dy, and dz are individually infinitesimally small, the surface area of the surface two of these quantities create will be infinitesimally small as well. And the volume of this whole cube will be infinitesimally small as well. Because all the quantities are in the range of, as I said earlier, 10 to the power minus 53 or 10 to the power minus 65. So let's say we're talking about this surface over here, which is BCRQ. Let's say this is a really small surface, and this rectangular surface is created by a length of dx and a height of dz. So if you just look at it from this direction, you will see a rectangle, the length of which is dx and the width of which is dz. The surface area of this infinitesimally small surface over here will be given by ds equals to dx dz. Now we have a little subscript that we have to use over here, and to understand that, let's introduce a concept that you should all be familiar with already. That is, in general cases, we treat a surface area as a scalar quantity. Let's say this is a surface which has a value of 5 meters square or something like that, and generally we treat it as a scalar quantity, okay? But in times, in electromagnetics, we have to treat the area as vector quantities. And how do we do it? Any vector should have a direction, right? And in case of area vector, the direction of the vector is perpendicular to the surface, okay? So if this is a rectangular surface, the direction perpendicular to it will always be the direction of this vector. So if we treat the area as a scalar quantity, we just write it as 5 meters square. But if we treat it as a vector quantity, then we write it as 5 to the direction an meters square. This is just the vector notation. Okay, so back to the usual case. Now we are treating the BCRQ rectangular area over here, and we just found out that its value is like this. Okay, now if we were to treat this area as a vector, then the direction of the vector should be perpendicular to this surface. Okay, so if you look at this picture over here, the perpendicular direction to this surface would be directed to the y-axis direction. All right, and the unit vector associated with the direction of y-axis is given by ay. So if you were to transform this vector into this area into its vector notation, you just write it as its value and the unit vector that it's pointing towards. Okay, since this vector over here is directed to the y direction, so we separate this notation with a subscript of y. Similarly, if we take a look at this surface over here, the ABCD surface over here. This is comprised of dy and dz, right? So the area of this surface will be dy dz, and the perpendicular direction to this surface is along x-axis, right? So if we translate it into the vector quantity, then we get ax. And since this is a vector now, we apply a bar over it and a subscript of x to denote that it's the uh, surface that's perpendicular to the ax vector, all right? And finally, if we look at the top surface over here, which is PQBA, that surface comprises of the dx quantity and dy quantity, and it's still rectangular, so d is the value of the area of the surface is given by dx dy, and the direction perpendicular to it is directed along the z-axis. So if we translate this into a vector quantity, we get the sz. Okay, so these are the differential area quantity that you will be using. And finally, the differential volume is just the volume, small volume created over it by the rectangular parallelepiped. Okay, you already know the formula of the volume of a rectangular parallelepiped, right? If it's given by the sides of x, y, and z, the volume will be given by x, y, and z, right? So the differential volume that we're getting over here, dv, is equals to dx, dy, and dz. And unlike the differential area, volume is only a scalar.